This video is about relative density disequilibrium, and it's a demonstration of whether a vacuum chamber floats or sinks in water. And we're going to talk about what the buoyant force predicts, or what relative density predicts, what gravity predicts. Okay, let's see.
Now let's check out what happens to a vacuum chamber in water. And hey, you can even do this same experiment when you get your very own vacuum chamber in your first subscription box. Okay, let's get a
Shout out to Action Lab. I don't always agree with his explanations, but I like what he does. So that's the name of this channel, is Action Lab. If you want to see all his experiments, subscribe.
vacuumed out. 3, 2, 1. Okay, we're a full vacuum. Let's go ahead and see if it floats, and then let's open it up under the water. Okay, does a vacuum chamber float? 3, 2, 1. It definitely floats.
Now, it definitely floats. We just seen that. So their explanation would be the volume. Okay, the buoyancy explanation would be that the volume of it's displacing the water. Okay, but the volume, okay, and the density of it, the density of the volume. Okay, but wouldn't a vacuum chamber be the same as if I took the four walls of that acrylic and the metal valves and all that and just squeezed them together? Because if I did that, if I just put all the walls and just condensed it to get rid of the chamber, basically, it would sink. The acrylic and the valves and all that, they would sink. Okay, and there's no mass inside of the vacuum chamber. It's a vacuum. There's no mass. So what's making it float? Okay, listen to their explanation first.
I don't quite understand why people would think that the vacuum chamber would sink when it's under vacuum, because actually it's even more buoyant now than when it had air in it, because you don't have the weight of the air pressing down, so it floats even higher than it would with air.
He's spot on, and that's a relative density answer. Okay, do you think that little bit of air would make a difference in the weight of it? Okay, but he's still spot on, because the vacuum is less dense than the air inside of it. So if you had helium inside of it, it would be more buoyant than if you had, let's say, sulfur hexafluoride, to go extreme. It would be less buoyant with the heavier gas. So the vacuum is lighter than it all. So the vacuum itself fits in to relative density disequilibrium. And I'm going to give other examples of that.
Using something very light. I have here a balloon with helium in it and a little bit of duct tape on it. You can see.
So now I'm showing you the helium balloon in a vacuum chamber and their explanation, and how there is a glaring problem. A couple of them, really. And first, let's look and see what happens to a helium balloon in a vacuum chamber.
It floats. So let's see what happens if we put this in the vacuum chamber. Okay, does a balloon get heavier in a vacuum? 3, 2, 1. And drop.
Now, the first glaring problem there is when he gets down to a vacuum, or right there near it, then that balloon is supposed to fall at the same speed as a lead ball. And as you see, it barely trickles down. I could also argue that he's having to use a really small, strong water balloon, because the helium wants to be filling that entire container. Okay, so if he's tried it with other balloons, and they would pop. Okay, so you could argue easily that he's compressing the helium inside that balloon, making it more dense. But either way, the density of a vacuum is less than that of helium. So it finally trickles down. Now listen to their explanation. It's laughable, but nothing against Action Lab, man, but this is the narrative we get.
See that? It dropped off the top. Now let's let the air back in. And it floats back up. So cool. So we have it right there at about 0.6 atmospheres. But if we reduce the air pressure in there, make it more of a vacuum, and it sinks.
Once again, look at it trickle down in the vacuum. Not racing down like it's supposed to. They say that the air is what separates, like dropping a golf ball in a ping pong ball. They say it's the resistance. So in a vacuum, the feather and the bowling ball are supposed to fall at the same speed. Well, you see there that the mass of the balloon is not going to fall ever. With helium in it, it's never going to fall at the same rate as a lead ball. That's horse shit. It's obvious. We need to update some shit, people.
Okay, so why did this happen? Why did the balloon just sink when we made it a vacuum in there? To take a cubic foot of air into space, not in orbit, but just in space, so you still have gravity, and weigh it on a scale, it would weigh around 36 grams. And
so that's a bold claim there. That's their explanation. So when they let the air, when they suck the air out of the chamber with the helium balloon, so what he's basically telling me is that the air all came from the top and the helium floated, like as it started to go down, it's floating on the air. In other words, the air left in there is just floating at the bottom and the helium balloon's still floating on it. And until the air comes out from underneath it, that's when the helium balloon sinks. But come on, common sense, people. We know better than that. And the fact of their air having weight, I got one more glaring problem to show to pretty much put the icing on the cake as far as air having weight.
That has a good resolution that I can pick it up, but also can take the full weight of the vacuum chamber. So the resolution of this scale is 1 gram. So let's turn on the vacuum chamber and see if it starts dropping in weight. Okay, seeing if a vacuum chamber weighs less with no air in it. It's now at 3,423 grams. So I'm going to zero it right here. Okay, it's now at 0 grams, so we'll be able to tell if it goes into the negative now. Okay, 3, 2, 1. Oh, wow. That's awesome. You can easily tell. Look at it just start dropping in weight. I did not expect it to show up that vividly. We're at half an atmosphere, it's already lost 24 grams.
So remember that. Half an atmosphere, it's lost 24 grams. So, because what he does next is he gets a pressure tank and fills it up. So 24 grams of air, half an atmosphere. Now, let's see. So, because I can make the argument that the vacuum is less dense than the air. So that's why it's lighter. Because he's evacuating the air, leaving a less dense vacuum, making it lose weight. And here's my evidence for that.
So you notice right off the bat it loses most of the weight. But now it's slowing down. We're at 0.2 atmospheres. Okay, we're at 0.1 atmospheres. We've lost 25 grams. Okay, so we're at a full vacuum now. And it's stayed at minus 25 grams. Oh, minus 25 grams, I'm gonna open it. is lost right at the beginning when the needle's about only 1/10 or 2/10 of the way down.
So when he took out half the atmosphere, it weighed 24 grams. Okay, it changed 24 grams. And the other half of the atmosphere only changed it 1 gram. Okay, that doesn't seem to fit the math, but it gets better. So listen up.
When we actually pressurize a chamber, will the weight increase then? Okay, increasing pressure. 3, 2, 1.
Pretty similar size chambers. I think the pressure chamber might be a little bit, I don't know. They look about the same. It's fair to make a estimate with.
Two atmospheres, 3 atmospheres, 10-gram increase.
So 3 atmospheres now, and only a 10-gram increase. 3 atmospheres. That's 6 times as much as his half an atmosphere, which was 24 grams differential. So half an atmosphere in his vacuum chamber changed it 24 grams, but 3 atmospheres, adding pressure, only added it 10 grams. Now, I mean, I'm not a mathematician by trade, but come on, people, does that add up? Okay, we got to rethink all this. So, off what I've showed you, just, we got to think of the solution. I think they're right there in front of our face. Just got to refine them. And they want math. Let's try and give them some math. I don't know. I think the point's made clearly. How about you? Let me know in comments.
12 grams, 15. So it's increased 14 grams. It's at 3.5 atmospheres, 15 grams. So in this case, when you add air pressure, it increases the weight.
So, and last but not least, the vacuum chamber underwater had one more point. It almost left off, but I think you'll enjoy this.
Okay, let's get it sinking. Okay, I'm gonna open it up. 3, 2, 1. Okay, I'm gonna open it up. 3, 2, 1. But the pressure isn't going up at all.
So the pressure isn't going up at all, even though he's putting water in there. So he's filling the vacuum tank with water, underwater obviously, but the pressure ain't going up. Okay, which I guess that could be expected, but here's the punchline.
See the pressure? Still a low vacuum. I'll let you think about why that is. So you can see there's no air bubbles coming out of this, but we're just filling up the volume. Whoa. Sucks in my finger. Whoa, there's like strong pressure waves shaking the whole vacuum chamber. So it's interesting, the bubbles that you see in there are not actually air bubbles. It looks like it's shooting in, making air bubbles, but it's actually nothing bubbles. I mean, there's
Nothing bubbles. You hear that? Nothing bubbles.
a little bit of air in there, but it's pretty much, these are bubbles of vacuum.
So bubbles of vacuum. So that shows, so a vacuum is still something, people. I mean, this is a good way to me to end this video, because even if there is a little bit of air, whatever, then it wouldn't be that much. I mean, that's vigorous. Even if you could say it's boiling, okay, once again, not nowhere nearly that much, because the air he winds up at the very end, at the top, It's barely any. He's got a teeny little bubble at the top. It's completely full of water and not air. And I wish he'd show us what happens when he opens it up. Maybe he does, but so even empty space takes up space. So there's no such thing as nothing, people. There's no such thing as a void. I think that's what I got from that. He's calling them bubbles of nothing, but they're taking up space, obviously.
Okay, so you can see it's completely filled up now. There is a little air bubble up top here. So essentially this is how much air was left in the chamber when it was under vacuum. So what was interesting about that is it could fill up with water without letting any air bubbles out. So let's see what